Welcome to Tech I Spy. Today, we step slightly into the future. Not far into science fiction. Just a few careful inches beyond the edge of what is commercially available today. We are looking at a company called Leap 71, a private engineering firm that is building something unusual. Instead of designing machines with human engineers, they are developing a large computational engineering model that generates the geometry of engines, thermal systems, and structural components directly from physics and manufacturing rules. In other words, an artificial intelligence that designs real machines. This episode treats Leap 71 exactly as we would treat any major technology company. You are getting a full and detailed SWOT analysis. But it comes with an important note. This is a company on the horizon. It is private. It has no public stock. And much of what it builds exists as early prototypes, concept demonstrators, or laboratory scale tests. Yet it is interesting enough and potentially disruptive enough that it deserves a place in our series. If Leap 71 succeeds, the impact will not belong only to them. Entire sectors will benefit. Aerospace, defense, electric propulsion, metal additive manufacturing. Even the companies that make industrial printers, simulation tools, and advanced materials will feel the pull of this technology. What makes this so compelling is the gap it attempts to close. Traditional engineering is slow and expensive. Complex hardware takes years of design work, multiple iterations, and long cycles of testing and revision. Leap 71 proposes a different path. Feed the model the physics, the boundary conditions, and the materials. Then ask it to generate the physical component directly. This is not science fiction. We have already seen early examples in small rocket engines, heat exchangers, and hypersonic pre-cooler structures. These demonstrations do not make the technology mature. They simply show that the door is now open. And behind that door is a chance to compress years of engineering work into weeks. In this episode, we explore what this means for competitive advantage. We look at which industries stand to gain. We highlight the weaknesses, including the long road to certification, the reliance on large format metal printers, and the uncertainty over the company's commercial model. And we consider the opportunities if this method becomes normal. Faster design cycles, new geometries shaped by physics rather than human habit, a new relationship between artificial intelligence and physical hardware. This episode is speculative, but it is grounded. Everything here is based on public demonstrations and verifiable engineering principles. The future arrives in small footsteps. Today, we follow one of them: strengths. The strongest quality behind Leap 71 is the depth of engineering logic embedded in its model. Most artificial intelligence systems today are trained to predict language, images, or patterns in data. They are not trained to understand heat transfer, structural loads, fluid dynamics, or the realities of manufacturing. Noyron, the engine that drives their work, is different because it has been built from the ground up to encode the rules and principles that govern physical machines. This gives it an unusual power. It does not create shapes for the sake of novelty. It designs components that satisfy the laws of physics while remaining printable on real-world industrial metal systems. That combination of physical correctness and manufacturing awareness is rare, and it allows the company to generate geometries that humans simply do not conceive. Another strength lies in how the model collapses time. A conventional design cycle requires individual specialists for fluid analysis, thermal modeling, structural verification, and manufacturability checks. Each team produces its own set of files, and each revision requires coordination and negotiation. Leap 71's workflow bypasses this separation. The model already contains the thermal assumptions. It already understands where material needs strength, where coolant must flow, and how a laser powder bed fusion machine will behave during printing. When a design emerges, it is already complete. This is the type of strength that turns a multi-year development project into something measured in days or weeks. If this advantage continues to grow, it may become one of the most powerful differentiators in engineering for the next decade. A further advantage is the way the company pairs its model with large format additive manufacturing companies. These partnerships allow them to produce structures that would be impossible using traditional techniques. The hypersonic pre-cooler concept, for example, uses a folded fractal geometry that offers a surface area far beyond what human designers would normally attempt. The reason it exists at all is because the model created it, and because an industrial printer large enough to build it now exists. This link between algorithmic design and metal printing is a strength that expands as the printers themselves evolve. Every improvement in printing speed, material science, or volumetric capacity becomes an immediate upgrade to the model's potential output. There is also strength in the company's philosophy. They are not trying to replace engineers. They are trying to remove the repetitive geometry creation that slows engineering down. Human experts remain essential because they define the constraints, the target performance, and the safety factors. The artificial intelligence is the tool that creates the thousands of micro-scale variations that would otherwise take weeks of labor. This makes Leap 71 a complement to the engineering world rather than a challenge to it. The firms that adopt these tools will be firms that move faster, innovate more frequently, and explore more ambitious architectures. Another strength is the clarity of their demonstrations. They do not produce slide decks or blurred renderings. They publish real hardware, engines that have been fired in controlled tests, complex structures standing taller than a human being, copper alloy components that show the fine internal channels and lattice work required for advanced thermal systems. This practical evidence gives credibility to their claims, even if the technology is still in its early stages. Finally, the company benefits from its position at the intersection of several rising sectors. Aerospace is searching for new propulsion architectures. Defense markets are investing heavily in hypersonics and thermal protection systems. Energy sectors need more efficient heat exchangers. The electric mobility world needs novel cooling methods for batteries and power electronics. Additive manufacturing companies constantly seek impressive demonstrators to prove their machines can handle high complexity and high reliability. Leap 71 sits in the center of all of these currents. If the model continues to mature, the company will find itself pulled forward by demand from multiple directions. Weaknesses. The most immediate weakness facing Leap 71 is the immaturity of the technology when measured against the standards required for operational aerospace and defense hardware. A component that looks promising on a test stand or in a laboratory is not the same as a certified engine ready for flight. The gulf between a prototype and a qualified system is enormous. It includes thermal cycling, vibration testing, fatigue analysis, material validation, lifetime predictions, and the careful accumulation of failure data under controlled conditions. Traditional aerospace companies have built these processes over decades. Leap 71 has impressive prototypes, but it has not yet demonstrated that its method can pass through the long and unforgiving qualification pipeline that governs anything placed on an aircraft, a missile or a space vehicle. This is not a criticism of the concept. It is simply the reality of the certification landscape. Another weakness comes from the fact that the company is entirely reliant on metal additive manufacturing, and not just any type of printer. They depend on some of the largest and most advanced laser powder bed fusion systems ever built. These machines are expensive, slow, and extremely sensitive to build parameters. A printer capable of constructing a tall, complex, monolithic copper component is not a common piece of equipment. It represents a small global supply. That means production capacity is limited and vulnerable to the strategic priorities of the printing partners. If one of these partners shifts focus, changes pricing, or experiences technical setbacks, Leap 71 would feel the shock immediately. Their models can generate extraordinary geometries, but those geometries are worthless if they cannot be manufactured consistently at scale. A further weakness lies in the absence of a defined commercial structure. Because the company is private and its platform is not sold as software, the long-term revenue model is unclear. It is difficult to determine whether they plan to operate as a design studio, a licensing provider, a manufacturing partner, or a hybrid of all three. This uncertainty makes it hard to judge how the business scales. A design service can generate interest, but may never produce the recurring revenue needed to finance growth. A licensing model requires customers who trust the model enough to use it for real projects. A hardware manufacturing path demands capital, factories, and supply chains. Without clarity, investors cannot easily evaluate the company's financial trajectory, and potential industrial partners may hesitate to build their own roadmaps around it. There is also the challenge of trust. Many engineers are cautious when presented with artificial intelligence systems that claim to outperform traditional methods. They want traceability, error bounds, and the ability to examine every assumption. Noyron may be powerful, but it is still a black box from the perspective of a certification authority. If the model produces geometry that performs well in tests, that is encouraging. But aerospace regulators will want to know exactly why the shape works, what physical assumptions were made, and how the system responds when pushed beyond its design limits. This demand for transparency could slow adoption, especially if the company cannot provide interpretable internal logic. Another weakness arises from the company's limited track record. It has only a few years of history and only a handful of public test results. There are no long-duration studies, no multi-year field trials, and no fleets of engines using its methods. Competitors in traditional engineering have vast data archives filled with operational results and documented lessons. Leap 71 does not yet have the luxury of that institutional memory. Without it, every new project becomes a fresh attempt to prove that the technology is trustworthy. Finally, the company faces the structural weakness of being ahead of its time. Many industries are not yet ready to adopt algorithmic geometry generation. They still operate with legacy software, legacy design cultures, and legacy procurement models. Even if Noyron produces better designs, the organizations that might use it are often resistant to change. They are comfortable with the familiar sequence of drafting, simulation, revision, and review. Convincing them to shift to an artificial intelligence-driven approach could take longer than expected. Opportunities. The greatest opportunity created by Leap 71 is the potential shift in how complex machines are conceived. If an artificial intelligence model can generate physical components that respect thermal thresholds, structural loads, and manufacturing constraints, then the entire design cycle of aerospace hardware begins to change. Imagine a future in which a company can move from concept to prototype in a fraction of the time required today. This is not just about speed, it is about freedom. Engineers will be able to explore architectures that were previously abandoned because the geometry was too difficult to produce or too slow to evaluate. The opportunity lies in unlocking new design spaces, new propulsion architectures, new cooling methods, and new structural forms that the traditional workflows did not have the capacity to explore. Another opportunity comes from the rising demand for high-performance thermal systems. Hypersonic vehicles, reusable launch systems, high-power electric aircraft, and next-generation energy platforms all require cooling systems that can operate under extreme conditions. The fractal pre-cooler concept is only one example of what becomes possible when design is no longer limited by human intuition. If the model can generate heat exchangers and thermal components that outperform legacy systems, then Leap 71 could become a supplier to sectors that are desperate for innovation. Thermal management is one of the least glamorous but most essential areas of modern engineering. There is enormous value in making even modest improvements, and this technology hints at far more than modest gains. There is also opportunity in the expanding landscape of metal additive manufacturing. Large format printers are growing in scale, reliability, and material diversity. Every year, the machines become more capable. As they grow, they allow models like Noyron to produce ever more ambitious components. This relationship between computational design and industrial printing is a positive feedback loop. Better printers allow more complex designs. More complex designs demonstrate the potential of the printers. As this cycle progresses, Leap 71 stands to benefit from an industry that is undergoing rapid transformation. The company can position itself not only as a creator of components, but also as a driver of demand for the next generation of additive manufacturing equipment. A further opportunity emerges from the defense and aerospace sectors, which are entering a decade characterized by increased budgets and new priorities. Hypersonic platforms need new engines. Reusable boosters need lighter and more efficient hardware. Military customers require systems that can be produced faster and modified quickly in response to new threats. Traditional development cycles are too slow for the pace of modern conflict. A system that allows rapid iteration with physical realism could become incredibly attractive to defense contractors and research organizations. Even if the model is not ready for final deployment, it can still accelerate early design phases in high-value programs. There is also long-term opportunity in industries outside aerospace. Power generation, industrial compressors, advanced automotive applications, and even medical devices depend on components where fluid flow and heat transfer are critical. The company's method could eventually influence any sector where geometry and physics interact. The industrial world is full of complex systems that were designed decades ago and have barely changed because the cost of redesign was too high. If design costs fall and design speed rises, entire categories of hardware can be reimagined. This is the quiet opportunity that surrounds Leap 71. Not the dramatic prototypes that attract headlines, but the slow and steady reform of machines that underpin the modern economy. Another meaningful opportunity lies in the educational and professional shift that will occur as artificial intelligence becomes more embedded in engineering practice. Universities and research institutions may be interested in collaborating with companies that can demonstrate computational engineering methods. Early access programs, joint research initiatives, and government-funded technology trials could help the company grow its influence without needing the financial structure of a traditional manufacturer. These relationships would also validate the method in the eyes of regulators and certification agencies, smoothing the path to future adoption. Finally, there is an opportunity for Leap 71 to define an entirely new category of engineering. If the company continues to publish demonstrators and continues to show that complex physical systems can be generated from structured models rather than manual drafting, then it may become the reference point for a new generation of design tools. In the long term, this is perhaps the most important opportunity of all. Not the production of a single engine or component, but the establishment of a new norm where physical machines are created by artificial intelligence trained on the rules of the universe itself. Threats. The most serious threat facing Leap 71 is the unforgiving reality of aerospace qualification. Many technologies begin as promising prototypes and then grind to a halt once they encounter the long chain of certification steps that lead to real flight. To survive that process, a technology must be repeatable, predictable, and fully understood by regulators. If the artificial intelligence generates geometry that performs well but cannot be explained within the existing certification frameworks, then approval becomes slow and uncertain. A single failed test or unexplained failure mode could delay adoption for years. No matter how powerful the model is, the aerospace sector will not compromise on safety or traceability. This structural conservatism exists for good reasons, but it is a threat to any revolutionary design method. Another threat comes from the dependence on additive manufacturing infrastructure that the company does not directly control. The large format metal printers required to build their components are produced by a small set of industrial partners. They are expensive, power-hungry, and sensitive to fluctuations in global supply chains. If geopolitical tensions restrict access to advanced metal powders, or if industrial printer companies shift their focus to more profitable sectors, then Leap 71 could face production bottlenecks. A breakthrough design is only valuable if it can be manufactured reliably, but that reliability rests partly in the hands of external firms. In a world where supply chain stability is becoming increasingly fragile, this dependency is a genuine strategic threat. There is also the threat of internal complexity. As the models grow larger, they require more computational power, more structured physics knowledge, and more carefully managed data sets. This can create a situation where the company becomes trapped by its own architecture. If the model grows faster than the team can maintain and interpret it, errors could emerge in subtle ways. A miscalculated thermal boundary or an overlooked material constraint could propagate through multiple design cycles. Machine-generated complexity is impressive, but it is also opaque. Without internal systems that guarantee absolute quality control, the company risks losing confidence in its own output, and customers will notice that loss of confidence immediately. Competition poses another significant threat. Traditional aerospace companies may appear slow compared to an artificial intelligence-driven design studio, but they have vast resources, large research departments, and deep relationships with governments. If these incumbents decide to build their own computational engineering tools, they could accelerate quickly. They already possess the materials knowledge, the test facilities, the simulation departments, and the long institutional memory that Leap 71 lacks. Once the idea becomes mainstream, the advantage of being first may be short-lived. The threat is not competition between equals. It is the possibility that a major aerospace firm will replicate the method with far greater resources and far deeper customer access. There is also the emerging threat of regulation. As artificial intelligence becomes more tightly controlled, governments may impose rules on how algorithmic models are used in safety-critical systems. A regulatory framework designed for general artificial intelligence could unintentionally make life difficult for companies developing specialized engineering models. Restrictions on training data, transparency requirements, or certification rules for model updates could slow the development of computational engineering systems. If the company is forced to reveal its proprietary methods or justify every internal logic pathway, the regulatory environment could become hostile rather than supportive. Another threat is the potential mismatch between public perception and technical reality. The idea of artificial intelligence designing rocket engines will attract attention. It will also attract criticism. Engineers, investors, and journalists may form unrealistic expectations, and any setback could be interpreted as failure rather than natural maturation. When a technology is positioned at the edge of public imagination, it becomes vulnerable to narrative swings. A single underperforming test or a misinterpreted demonstration could damage the company's credibility far more than it would damage a traditional engineering firm. Managing that narrative becomes a strategic challenge in its own right. Finally, there is the long-term threat of stagnation in the markets the company depends on. If demand for hypersonic platforms slows, if reusable launch vehicle investment contracts, or if metal additive manufacturing enters a period of reduced growth due to economic pressures, the opportunities available to Leap 71 will narrow. Emerging technologies often move in waves. If this wave breaks before the company reaches commercial maturity, they could find themselves with extraordinary capability but insufficient demand. Conclusion. What we see in Leap 71 is not a finished company. It is a sign of what the next era of engineering may look like. The prototypes are early, the certification pathway is long, and the commercial structure is still taking shape. Yet something important is happening. The model at the heart of their work is showing that artificial intelligence can generate real hardware that respects the same laws of physics human engineers must follow. It is demonstrating that geometry can now be explored at scales and in forms that were once impossible to design by hand. It is hinting at a future in which the pace of innovation accelerates far beyond what traditional workflows can manage. Whether this company becomes the leader of that movement or simply one of its early pioneers remains to be seen. What matters is that the door is open. Computational engineering, as presented here, solves a problem that has constrained industry for decades. It offers a way to break free from slow iteration cycles and from the limits of human intuition in complex thermal and structural systems. If these ideas are refined, expanded, and supported by growing additive manufacturing capability, then the impact will extend across aerospace, defense, energy, electric mobility, and even advanced industrial equipment. This analysis has been speculative, but not in the sense of fantasy. Everything we have discussed is grounded in real demonstrations, publicly documented hardware and principles that align with established physics. The speculation comes from looking forward, from recognizing that the world is changing, and from understanding that companies like Leap 71 can influence sectors even before they reach commercial maturity. They create momentum simply by proving that new paths exist. For now, this is a company to watch. Not one you can invest in, not one with a stock code, but one whose ideas may quietly influence the machines of tomorrow. If they succeed, they will help shape a new era in design and manufacturing. If others adopt their methods, the transformation will be even larger. Either way, the horizon has shifted a little closer. Thank you for watching, and as always, stay curious